Can we get started? Okay, this is part 2, but I'll quickly go through part 1 as a reminder and for people who weren't here. So the fundamental concept is follow the photons, follow the money, follow the photons. And if you track the photons from where they come, where they end up and what happens to them on the way through, then you can't go wrong and you'll understand everything a lot better. So the fundamental concept is we're collecting photons, and the more photons we get, the better the images, and it's that simple. And photons are related to the aperture squared, which is the area, times the exposure, and that's the aperture of the telescope. And the signal to noise ratio is related to the square root of the number of photons you collect. So those last 2 lines on that slide are what it's all about. So differences from daytime. In daytime, when you increase the ISO of your camera, you get a lot more noise, but that's not because you've increased the ISO, it's because you've halved the exposure, which means you've halved the number of photons you collected. And in daytime photography, changing the F ratio actually changes the aperture, but in astrophotography, when you change the F ratio, you're not changing the exposure. You're not stopping down your mirror or your lens. What makes a good astrophoto? Signal to noise ratio, which is the ratio of signal to the noise. So quick examples, that's signal to noise ratio of 0.5. Can't really see much. 1, 5, 20. Now you're starting to get good images. So you want to aim for a signal to noise ratio of 20 and above. That's 100. I'll go backwards. 20, 100. Slight improvement. And then that's infinity, where there's no noise at all. In colour, 5, 20. So you want a signal to noise ratio of at least 20, between 20 and 100. You won't get infinite because there's always noise. So telescope is a funnel. It funnels the photons onto your sensor. And the focal length, the longer the focal length, the less the field of view. So you can see up there that 2 degrees field of view for a long focal length compared to 4 degrees field of view for a shorter focal length. People say that a short focal length is faster, but it's not, because it's not changing the aperture and it's not changing the rate that you're collecting photons. All it's doing is focusing the photons that you get onto a smaller area of the sensor, which makes it appear to be brighter, but it's not changing the signal to noise ratio because you're not changing the number of photons that you're collecting. So if you're collecting a little tiny area of the Orion Nebula, then the signal to noise ratio is the same because you're collecting the same number of photons from that area. Signal is where the information is, and you can't, I know, I won't cover that. Noise is not unwanted photons. So, for example, a cosmic ray strike is not noise. It's just unwanted signal. Same thing with satellite trails, light pollution, they're signals. So what is noise? So noise is uncertainty in the signal. So we need to look at statistical sampling theory. So what's happening is that the Orion Nebula is putting out untold number of photons, and you're collecting some of those photons. So you're sampling the photons that it's putting out. So it's a sampling situation. We're familiar with sampling situations because of, say, opinion polls. So up there, Labour is 37% and National is 34%. We sampled 1,000 people out of 5 million in New Zealand. So it's the same as taking a photograph of the Orion Nebula. We're sampling a small proportion of the photons that are coming from that nebula. So this says labour is 37% plus or minus 3%. 3% is the noise. It's the uncertainty in the signal. So here the signal to noise ratio is 37 divided by 3, which is 12.3. So the important concept is the noise is the uncertainty. So collecting more photons is like sampling more people. The more you collect, the more an accurate picture of the Orion Nebula you're going to get. So I'll just talk that. The noise is a standard deviation, if you know the formula for standard deviation. If you don't, then this is a picture. The signal is the mean of your distribution of photons, and the noise is the standard deviation of that signal. I've already covered that. So there's various noise sources. I'm not covering those. So photons arrive in a random way, and the analogy I use is like raindrops falling on concrete. They scatter around, and the more you get, the more you start getting the pattern. So you can see here that in the top left, it's like raindrops on the concrete, and then the more you get to the bottom right, you start getting the picture. So that has a statistical property that the standard deviation, which is the noise, is the square root of the signal. That comes from the Poisson distribution. So that's where the formula that the signal to noise ratio equals the square root of the number of photons comes from. F ratio myth, people believe that small f ratio is faster, but it's not faster at collecting photons, so it's a myth. ISO myth, higher ISO gives you a brighter image, but it's not changing the number of photons you're collecting, so it's not giving you a better quality image. These myths aren't true. They relate to something that happens after your telescope lens or mirror has collected the photons. So they're post-processing steps. And you can't post-process an image to collect more photons because that doesn't work. You've already collected them. So yeah, I'll explain this again. I explained it last time, but I'll explain it again. You have a long focal length. Your image appears to be very faint, and that's an example. Short focal length image appears to be bright. So this is where the myth comes from. People say, oh, it's a brighter image because that's brighter than that. But both images come from the same number of photons. So they're the same quality of image, except in this one, you've lost a little bit of resolution. Now, this brighter image can be achieved in software because it's a post-processing step. And you can post-process this image using Photoshop to get this image. So you're simulating the F ratio shortening. And that's what you get when you post-process. It's exactly the same image because you've captured exactly the same photons. But there is a difference in that a smaller F ratio gives you a wider field of view. So that's an important point. It doesn't give you any more photons from the area you're photographing, but it gives you a bigger area that you're photographing. And that's the main reason to have a small F ratio. It's not because it's faster. So I'll just explain that. The ISO myth. ISO is post-processing done in the camera. What the camera does is just if to go from ISO 100 to ISO 200, the camera just multiplies every pixel value by 2, which is a stretch. And an ISO stretch just multiplies every pixel by 2. That's not what you want, because for astronomical purposes, you want to multiply the dim parts of the images by more than the bright parts, because the bright parts are the stars, and you don't want to multiply them any further. You want to keep them the same. So an astronomical stretch is this one here, where the brightest stars get no stretch, and the dimmest nebulosity gets most of the stretch. But this is an ISO stretch, and so you get clipping at the top. In other words, you lose information at the bright end. So you lose the colour of the stars, and the stars become bloated, they become bigger in size. And something else happens, which I'll explain later on.
So, I'm shooting in RAW, I'm shooting on my Canon camera, but I set the ISO before I go out. Is that just the ISO just an amplification?
That's all, yeah, it's just an amplification. And you don't want to do that in the camera. You want to do it in Photoshop or PixInsight or whatever. So you can do a proper stretch instead of an ISO stretch. So I say that any ISO greater than 100 is no longer RAW. And you really want, for astronomical purposes, to have a raw image, as raw as possible, as close to what the sensor captured as possible. So increasing ISO reduces the dynamic range of the image, and I'm going to explain that in part 2, which is today. So reduced dynamic range means you lose star colour, you get bloated stars, and you reduce the possible signal-to-noise ratio that you can get. So this is the example I gave last time. This is what the jewel box cluster is supposed to look like. And at Waharau a few months ago, Alex took these images with his Sony camera, and at ISO 6400, you can't really see the orange in that star there, but if you reduce the ISO to 100, you can see that there is an orange-red star there. You can see that the stars on the left have less colour and are bigger. What you can't really see is that there's less signal-to-noise ratio in that image as well. And this is a good example because a lot of these Sony people use this particular camera, the Alpha 7 III, at ISO 6400. And it doesn't make sense to me. You should use it at 100. And this is the proof. This is practical proof plus theoretical proof as well.
There is actually one thing I would say. So a lot of the modern digital camera, they have two-stage in their gains. So technically they have two native ISO. So the base ISO does have slightly better dynamic range, but it usually goes like this, and then they have a second jump up. So it can be beneficial if you're just using the start of the second stage. So for most of them are starting from about ISO 400. So if you actually did an experiment, you find that 100 and 400 will behave differently, but their performance wouldn't be too well.
Yeah, well, I'm going to explain that later on, and I'm going to explain why what Eric has just said isn't correct.
Ooh, okay.
So we're up to dynamic range. This is where we got to last week. So dynamic range is the ratio of the brightest star you can image to the faintest star that you can image. So it's just a natural, intuitive concept, the difference between the brightest and the dimmest. But it has a slight trick to it because the dimmest star gets lost in the noise from the electronics of the camera. So the dimmest star you can image isn't a pixel value of 1. It might be a pixel value of 3 because of noise. And that noise is noise contributed by the electronics of the camera. Most of it is called read noise, but there is other noise. And the brightest star you can image is probably, for a DSLR, 2 to the power of 14, or 2 to the power of 16 if you've got a good astronomical camera, or the full well capacity, which I'll explain later on. So it's the intuitive concept of the difference between the brightest and the dimmest that you can see. Now, the difference between the brightest and the dimmest is measured in various ways. It can be measured using stops, or EVs, or decibels, or the most useful measure for us is star magnitudes. So the greater the dynamic range, the greater the difference between bright stars and faint stars that you can image without blowing out the bright stars. Increasing ISO or gain decreases your dynamic range, and I'll explain why. But you already know, because increasing the ISO is post-processing and it doesn't do a very good stretch. It multiplies every pixel by the same value instead of doing an astronomical stretch, and that's the reason. So the bright stars get blown out and you lose colour and you get bloated stars, which I've already said quite a few times tonight. So the brightest star that you can image is equal to the full well capacity of your sensor. Your sensor is limited to the brightness that it can it's limited to 2 to the 16 or 2 to the 14, or however many electrons the well can hold. Anyway, here's the explanation.
When you say 2 to the... are you talking about photons? Are you talking about photons, or what?
I'll explain that now. So photons come in and they hit the sensor, and ideally each photon kicks off an electron, and then the electrons are stored inside the sensor, inside a well in the sensor. So this is example, this well is 1 pixel in the sensor. So it accumulates all these electrons, and this is a picture of all the electrons being accumulated. Electrons have a negative charge, and so the charge builds up, so it builds up a voltage, and then the circuitry uses a voltage, an analog to digital voltage converter, to convert the voltage into a digital number. And that number is arbitrarily scaled to 2 to the power of something. In this case, it's scaled to 4095, which is 2 to the power of 12, I think. Or in a DSLR, 2 to the power of 14, or an astronomy camera, 2 to the power of 16. So the brightest star that you can image is related to how well you can fill up the well with electrons. When the well gets full, it overflows, and that's when you have exceeded the capacity of the sensor and where everything goes white. Now, if you apply gain or ISO, what it does is it doubles the voltage. It doubles the effective number of electrons that you've got in the well. So here we've got an ISO of 200 or a gain of 2, and we've got something like 1600 electrons. It just doubles that number, and so we've got 3200 or 3199 electrons. So you can see that by applying ISO or gain, you're effectively reducing the capacity of the well because it's going to overflow a lot earlier. So that's the technical explanation of why that post-processing step done inside the well is a bad thing and why you lose dynamic range. We've automatically halved the dynamic range by using an ISO of 200.
Okay, so the reason you get those floated stars is that it's the, I guess the glow, it's the natural glow that's sort of around the stars.
That gets blown up.
They'll then overflowing, so
yep.
Expanding.
Yep. So all the faint part of the stars becomes bright. The bright part stays bright, can't go over higher than 4095 in this case. And so the star just gets bigger and bigger.
And any colour just goes white.
Yeah.
Well, the reason why it goes white is that you're measuring red, green and blue. And to have colour, the red, green and blue values need to be different from each other. You need more red than green and blue to get a red star. But as soon as the well gets full, then the red and the green and the blue are all equal to each other at 2 to the power of whatever. And when they're all equal, they're white. So that's a good question, that. So that's why everything goes white. That's why the stars get bloated, and why I haven't quite explained why you lose signal to noise ratio, but that's coming up. So this is my camera, and I've measured the dynamic range in star magnitudes versus ISO. So you can see that for ISO 100, you can measure about 11 magnitudes difference in star brightnesses. But by the time you got to ISO, I forget what this N value is, you've only can measure stars that differ from each other by 4 magnitudes. So that's the effect on measuring stars of reducing your dynamic range by increasing your ISO. 4 magnitudes isn't very much. It means if you're measuring magnitude 1 stars, then any star brighter than 4 will just be plain white. So this is an example of the Orion Nebula at 4 different ISOs. And you can see the trapezium. The trapezium doesn't have any colour, but it doesn't matter. You can see the 4 small stars. By the time you get to ISO 6400, you can see the bloating, and you can barely see that it's a trapezium at all. But people get excited by saying ISO 6400 because they say, oh look, you can see nebulosity now. You can see all this nebulosity. You can't see it there. But that's a false argument because all the photons are in the image. You haven't, this image doesn't have any more nebulosity than that. It's just that you need to stretch it to bring it out. So if we stretch all 4 images, we get something like that. And you can see that this ISO 200 has better colour and smaller stars than ISO 6400, where you can barely see the trapezium at all. So there's not a lot of dynamic range here, and so you're losing the trapezium.
If you're trying to find a very faint object as a real beginner, do you amp up the ISO so that you can locate the image very clearly? Because I'm still working with tracking and so on. So I find if something's very, very faint, I mean, horsehead and really sort of awkward. If I'll take a shot, I just thought about your speech a few weeks ago. I have to sort of amplify up the ISO, take 1 or 2 shots to ensure I'm actually to actually locate the image in the sensor. Does that make sense?
Well, what?
At 100, I can't see anything.
That's right. So you want to stretch the image, but you don't want to download it to Photoshop and do all that. So you get the camera to stretch it, and it can only do an ISO stretch, which is a pretty crude stretch. But that's good enough for you to tell what you're imaging, and it lets you focus. And I think good cameras these days let you amplify the image for focusing. I think Sony cameras let you do that, so they brighten it. And
So you're just looking on the screen of the camera.
I'm looking at the screen.
Yeah.
I'm looking at it on a horsehead. I'll amp it around sort of 10,000
Right,
or something,
yeah.
or I can then just about see it if I take a shot. Take a shot, about 30 seconds, and I can just about see it. Now we'll bring it down to the 100, knowing that I've located it. Otherwise, at 100, I don't know if I'm looking at the target. Ryan's not hard off, but anything like Rosette,
or anything, anytime you want to focus,
you just can't see it.
just up the ISO, yeah, because that's not,
Test shot.
yeah, it's not the image you're going to keep, but it helps you see the image on the screen.
And then, sorry, one other question. So just to clarify, so do you take as many exposures if you were doing, if someone was doing 1600 ISO and they took 100 subs of Rosette? Yeah. You're saying, look at 100, are you still doing 100 subs, or do you need to do more subs, or? I'm saying you shouldn't increase the ISO to 1600. I'm saying you should do it at 100. So you've got the same number of photons?
You at 16 or 100.
Or, right, okay. So you wouldn't need to increase the number of exposures or compensate?
No.
Okay.
People think, oh, increase the ISO, double the ISO, I only have to take half the exposures, but
Yeah, that's what I was just trying to clarify. Okay.
I cover that a little bit later on. So I take my full range of images at different ISOs, and I calculate the signal to noise ratio for that M42 image, for those M42 images, and you can see that the signal to noise ratio drops as the ISO goes up. And that's all you need to do. So that's all you need from tonight. Go home, just realize that, you increase the ISO, you're going to lose signal quality. And remember, this quality up here has exactly the same number of photons as that down there. It's exactly the same exposure. But because you've increased the ISO, you've lost signal to noise ratio, you've got lower quality images, and you've gained nothing for it. Increasing the ISO gives you absolutely nothing unless you're using test images to focus or frame. So my camera is just permanently set to ISO 200.
Tony, so does that come back to the square root of the noise part that you spoke of last week? That's why the increase in the ISO unproportionately increases. Oops, I don't know what that was. Disproportionately increases the amount of gain compared to the amount of signal compared to the amount of noise. They're not equally amplified, are they?
You've got less signal. I think the noise is pretty constant, the read noise.
Right, okay. But don't worry about that, I'll work that out myself later.
I do have something that may help. So when you increase, so say you go from ISO, assuming 100 is base, because that's not the same for all cameras. If you go from 100 to 200, your full well capacity halves.
Yes.
So your noise doesn't change. 3 electrons of image noise is still 3 electrons of image noise. Your readout noise is still the same. So So by cutting your well capacity by half, you're doubling the signal. Well, you're halving the signal to noise ratio because now the noise is contributing more by proportion.
Right, I
So
understand.
that's the artifact of having your well depth.
I would say you lose your detail. If you higher ISO, you lose detail. With all the wells are being filled up.
It's because, like, for example, right, if you have, say, your well depth is, let's just do a nice round number, 10,000. And at the lower ISO, you may be converting, say, 5 electron to 1 bit. But that's at 100. So if you now go to 200, you're now converting 2.5 electron to 1 bit. And it just keeps happening.
I understand.
Right? Yeah, so that's why your noise by proportion increases.
Yes.
Yeah.
Now, modern DSLRs and Astro cameras are CMOS, and they have, as Eric mentioned, 2 stages of amplification. So here, so this is ASI 2600. This is what Robert is using, and this is the dynamic range as a function of the gain. So what's happened here is that from here up to here, the sensor switches in an extra circuit which has an extra capacitor, and capacitor stores charge. So it's able to store more electrons. But the problem is switching in that extra circuit adds a little bit more noise. And this is this is what ZWO say their cameras do, their dynamic range as a function. So you've got high dynamic range here, and then it goes down low. Then they switch out the capacitor, so the full well capacity drops, but the noise drops even further, and so you get some of your dynamic range back, and then you start losing dynamic range. You can see here that Eric said that Sony users like to use their cameras here, but I'm not sure why, and I don't think that's a good idea, and I don't recommend it. And you'll see why shortly as well. But you can see that this dynamic range is less than that dynamic range. So why would you use this? Well, the reason people do it is because it's a higher gain, it's a higher ISO. It produces a brighter image. But, as I've explained 1 billion times already, it's a brighter image, but it's not collecting any more photons. It's not a better quality image. And that brightness can be achieved in software without the cost in dynamic range. So it has cost you a bit of dynamic range. So Sony users are using a bad argument. But the real test is actually to test.
What's your view on unity gain, though? But
It's
probably a topic for
irrelevant. It's irrelevant. Unity 1 is just an arbitrary number.
I guess.
Because 1 is just the same as 0.99. There's no, but that's more complicated to explain.
There's a quantization argument on that one.
No, but the thing is, it's an analog to voltage. It's an analog voltage to digital conversion, and there's nothing special happens at 1. But that's a bit more of an advanced topic.
That's a side question.
So this is an image that Robert took of the nebula with his camera. He took it at a range of gain values, which are ISO values. ISO and gain are the same thing. And I calculated the signal to noise ratio of each image and plotted it versus gain. So you can see what happens. You've got maximum signal to noise ratio here. It drops, then you drop out the capacitor, so you reduce the noise, so your signal to noise ratio goes up, but it goes nowhere near what you had at gain 0.
Okay.
It's strange that I can't really fully explain it. Why is this small change here from here to here reflected in such a big change in signal to noise ratio? This is a log scale, by the way, so it makes differences look smaller than they actually are. But this is the proof. Why would you ever consider a gain different from 0? It's a big difference in signal to noise ratio. For the same number of photons, remember, exactly the same exposure, you're throwing away a lot of the quality of the image.
So gain 0 just means no amplification.
Probably.
Right.
But there is an amplification to scale the number of electrons into the range of 0 to 2 to the power of 16.
Yeah.
But I wouldn't call that amplification, that's just a scaling. So I'm glad Robert gave me those images because this explains it quite clearly. Now that's signal to noise ratio. If we plot it on a log scale, we get a pair of straight parallel lines. So if you're mathematically inclined, then that's of quite interest. And they're quite straight lines. And the dots are exactly on the lines. So quite good imaging here, quite good images. So what that's a calculation by PixInsight, and I'm not sure what PixInsight does, how it does its calculation. So I took this image and I picked 4 areas: a bright area, a medium area, a dark area, and an edge area. And I did my own signal to noise ratio calculations just by taking the mean pixel value as the signal and the standard deviation as the noise. And I got exactly the same pattern. So I trust what PixInsight is doing. It shows exactly the same thing. Now this is the Sony camera.
Tony, one thing on there, just looking at the specifications for the camera, they don't actually talk about signal to noise ratio.
No, because that's a feature of your image.
Right, they just talk about...
They can only talk about dynamic range.
Yeah, right, and read noise.
That's right.
Yeah.
Interesting.
Because they don't know the signal noise either, the Poisson noise. So this is the Sony camera. Because people use it at 6400.
I will use it at 6400.
Yeah. This is your dynamic range here. 6 stops compared to 12 stops up here. Why would you use it at 6400 when you're losing all that dynamic range? Now, there's a relationship between dynamic range and signal to noise ratio. Dynamic range is the maximum signal divided by the minimum noise. So the maximum signal is probably 2 to the power of 16 or 2 to the power of 14. And the minimum noise is the read noise of the camera. You can't get below that. So, and also signal to noise ratio is the ratio of signal to noise in your image. And that formula looks exactly like the formula for dynamic range. So it turns out that the maximum signal to noise ratio you can get is the dynamic range. So that shows why reducing the dynamic... Is that me shutting down?
Your one, yeah, that is Robert's computer, unfortunately.
That's the warning.
The battery.
Hey, Bill, we just restart it. Yeah. It doesn't give you a warning, it just goes on going out.
So the maximum signal to noise ratio is equal to the dynamic range, and you can't exceed that. So if you're reducing the dynamic range by increasing your gain or ISO, you're reducing your signal to noise ratio. That's just from the definition of dynamic range. I can't remember what the next slide is.
Without time still.
But that's basically the gist of it.
Does this apply to film as well, like the bad old days when you have no choice but to use film and develop in a darkroom, and they use it when it's fast and when it's slow? Is it possible?
It's different though.
No.
Because in film the grain size actually changes, so you are actually changing the sensitivity. So digital ISO is a bit of see it as a volume knob. You're just changing the amplification, but film you're changing the physical property.
I believe, but I'm not sure, that in film, the bigger the grain,
The more sensitive, yeah.
I'm not sure if it's more sensitive because one photon sets off one grain. And so the bigger the grain, the more the effect on the emulsion one photon has. So
A little bit like binning, I guess, is it?
sort of, yeah.
Because the resolution does drop when you increase the ISO.
Yeah, it's kind of like
because of
binning
the
your
grain
CCD.
size, yeah.
But changing your film for different ISO is more akin to getting a different camera.
Yeah.
Yeah.
So after this,
Can you zip down? Yep. Keep going, keep going, keep going.
we're almost
Stop.
there. We're almost
Yep,
there.
back, up.
Oh, yeah, we're about here. Oh, we haven't clicked on that. Robert, you didn't click on it. No, if you go back and just go to the thing. Yep, we're there. Nice.
So for the same number of photons, the less the dynamic range, the less the signal to noise ratio, the less the quality of your images. You've gained absolutely nothing and you've lost a heck of a lot just by increasing the ISO above the native value. So I'll explain this.
This is a good one. I like this one.
You want to match the dynamic range of your camera to what you're photographing. But in astrophotography, what you're photographing always has more dynamic range than your camera. So imagine if that's the dynamic range of your image of what you're photographing, where this is dim nebulosity and this is bright stars, and this is the dynamic range of your camera, which is less. You can expose your camera for the bright stars and you lose the nebulosity, faint nebulosity, or you can expose for the faint nebulosity and all your stars up from here onwards get blown out and get turned white. So that's the challenge in astrophotography. There are some circumstances where there are some scenes that have a lesser dynamic range than your camera, and that can happen when you're doing narrowband imaging. So maybe imagine that is the dynamic range of your scene, and this is the dynamic range of the camera. What you don't want to be doing is using just the bottom part of the well. You want to use the full part of the well. In that case, you would increase the ISO or gain of the camera because you're not going to get anything blown out and you're going to get a finer resolution. So I just wanted to point that out, that the whole objective is to match this with this. And there are some circumstances where you want to actually shrink your dynamic range of your camera to match the dynamic range of the scene.
How would that affect the signal to noise ratio then?
It's not going to you're not going to lose anything because you're still capturing every single photon from the scene, and none of those photons are being blown out, and you're not losing any color, and you're not increasing the noise, and you're not reducing the dynamic range of the scene because your camera's got capturing the full dynamic range. And I had to mention that because people do narrowband imaging where you're photographing a very narrow wavelength, and those scenes can have, not usually, but they can have a low dynamic range. So, which ISO gain to use? Well, I've made that clear. And I've just said that. In any case, ISO 100 or gain 0 gives the greatest dynamic range. It gives you the best chance of getting the best signal to noise ratio. Now, some older cameras, especially Canons, produce less noise at higher ISOs. So those cameras should be used at about 800 or 1600 ISO because the gain in the noise reduction compensates for the loss of dynamic range. You still lose dynamic range, but you also lose some noise. So if you've got an older camera, just test things out, just like with Robert's images of the nebula. Do a few images at different ISOs and measure the signal to noise ratio, which is easy in PixInsight. So that's a summary. ISO, increasing ISO is post-processing. Don't let the camera do it. Do it yourself in Photoshop or PixInsight. You can't add any extra photons in post, so you can't add any extra photons by changing ISO. Which sub-exposure should you use? Is it better to do 10 30-second exposures or one 300-second exposure? Well, if you're reading your sensor 10 times instead of once, you're going to get 10 times the read noise. So you'll lower your signal to noise ratio. So it's better to have longer exposures than shorter ones if possible. But with modern cameras, the read noise is pretty small, and you probably won't notice the difference between 10 times 30 or 1 times 300 after you've stacked the 10 times 30. So it won't make much difference, and you probably won't notice it. In Auckland, light pollution contributes a heck of a lot more noise than the camera itself, and that's the main reason. So do 10 times 30 or 1 times 300. Depends on the quality of your mount and how well you can guide and things like that. There is a formula. If you do 10 times 30, you end up with 10 times as many images. So you've got to have more disk space, you've got to have more computing power. I try to do 15-minute images whenever I can because I can guide for 15 minutes and it saves disk space, saves computing time. So the lesson is that sub-exposure isn't that important. It used to be important in the olden days with CCD cameras where the read noise was much higher and it made a bigger difference. But for most of us using DSLRs or CMOS astronomy cameras, it doesn't make that much difference. So I wouldn't worry about it too much. There are more practical things to consider.
Tony, what about the thermal noise that obviously increases the longer your exposure? There must be some limit.
Yeah, but you compensate for that by doing calibrations.
Yeah,
so you still calibrate whether you do 10 times 30.
I was thinking if the thermal noise becomes such a large percentage of the well, you're basically narrowing your dynamic range, aren't you? Because you're leaving, say, if your well's, say, 64,000 deep, and there's 40,000 worth of thermal noise, then there's not a lot left above the noise.
Well,
So there must
thermal,
be some limit, but I don't know what it is.
your thermal noise is pretty small.
Right, so you'd have to take a really super long exposure.
That's right, of a very faint object for thermal noise to eat up your well. But technically you're correct, thermal noise does eat up the well, but you can ignore that, or we can ignore that. And if you've got an astro-cooled camera, then the cooling reduces the thermal noise even more. We haven't got time to have the fun with mathematics, but there's a formula for how to calculate the dynamic range in terms of star magnitudes, because stops are useless for us guys, because we are used to magnitudes, not stops. And this is some examples from Kumu, and an example of calculating the dynamic range and magnitude. So at Kumu we can image stars that differ from each other by 10.3 magnitudes in the same frame without blowing out any of the stars. Alistair, who's out there, lent me his sky sensitivity meter, and you can actually measure the light pollution. You can count the number of photons per second that come from light pollution. And if you go through all the calculations, you find that 1 hour at Kumu, which is where we have an observatory, is equal to 5 hours at Mount Albert in terms of signal to noise ratio. That's just due to light pollution. So,
Take one to set out too.
eh?
I thought you bought that little thing to Wahama and use it there. To collect the last March, was it last month? You took the little sky meter thing, didn't you?
Oh, yep, that's right.
Did you not use it there? What is it?
Yep, I use that to do these calculations.
How does that compare over that dark side?
Waharau is darker than Kumu, I believe, and so 1 hour at Waharau is probably equivalent to a whole night in Auckland.
Yeah.
In terms of signal to noise ratio.
Anecdotally, I think it is from past experience.
What's the reported sky number for Kumu? What's that for?
I think it's 3.5, and Waharau is 2, something like that. But those aren't scientific numbers. So Alistair's meter actually counts the number of photons, and it can give you the photons. So there's a calculation that you can do, and I've gone through it there, and there's a formula like 21.7 minus the sky magnitude and 3.87 times the blah, blah, blah. So I just wanted to show that it is possible to count photons from light pollution, and because light pollution is the biggest contributor to noise, then it's the biggest contributor to signal to noise ratio. So 1 hour at Waharau, it's really 3 hours because it's a 1 hour drive there and 1 hour drive back. But it's 3 hours for a night, beats a whole night in Auckland. But I haven't done the exact calculation. I've done it for Kumu.
Where is that up?
It's
Near Kaiawa on the Firth of Thames.
It's on the other side of the Lunar range.
it faces Coromandel.
Totally. I think we're just about running out of time.
I've run out of slides.
Oh, very good.
Nice.
Perfect timing.
That's a summary. That's the end.
Thanks, Tony.
Very good. Thank you.